Good morning, students. We're going to do 9.4 today. That is polar coordinates, polar graphs. There's actually a lot in this chapter, so I'm going to break it up into two separate videos. I should say a lot in this section. So I think I'm going to stick with all the plotting and the conversions for video 1. Video 2 then will be all the shortcuts that will enable you to graph polar shapes quickly without actually having to use a table to generate those ordered pairs. So here's a warm-up that I'd like you to try. Hit pause, work it, and then hit play. I'm going to work it now. All right, so I got a shape with vertices at 4, 7, 4, -3, and a focus at 4, 5. Got that labeled there, which means by using symmetry, I've got another focus at 4, -1. I got a center at 1, 2, 3, 4, 2. All right, well, we can start generating at least a portion of this equation. By the way, ellipse, correct? So my center's at 4, 2, which means I've got those two numerators, x minus 4 squared, y plus 1, the quantity squared, opposite day to the x and the y. Now I need to come up with the two denominators. I can get one quickly by noting that the distance from the center to the vertex is 5 units along the major axis, that is the y-axis, 5 units, which means this denominator is going to be 25. It's the square of that distance. I also know, since I don't know the length of the minor axis, but I do know the distance from the center to the focus points, that means 25 minus b squared has got to be equal to 3 squared, distance from center to focus, which means, of course, that b squared is equal to 16. And I've got it. All right, that's rectangular form. And then, of course, I'm going to use a Pythagorean identity that involves the sum of two squares. This, of course, is the sine squared of, we'll call it t, plus the cosine squared of t is equal to 1. By the way, addition is commutative. I don't really care which one you allot to x and which one you allot to y. I'll take either answer. So what you've got then is that the sine of t is equal to the innards of the first term, that is x minus 4 over 4. I then have the cosine of t being the innards of the second term, that is y plus 1 over 5, which means that my equation for x is going to be equal to 4 sine of t plus 4, and the equation for y is going to be 5 cosine of t minus 1. Again, the sines and the cosines, they're interchangeable. I'll take either answer. All right, so let's start section 9.4. All right, we'll start with polar coordinates. They are always written as an ordered pair, r comma theta. Polar graph paper, by the way, if you were lucky enough to have had the forethought to take your workbook home, starting on page 89, I've got a few pages, actually even earlier than that. In the back of the workbook, I've got several pages of polar graph paper, so help yourself to that. Yes, r comma theta. So if I ask you to graph the point 2 comma 3 pi over 4, if you remember Thomas the Tank Engine, the turntable, he would pull onto the turntable, the track would then rotate to whatever direction desired, and then he would either pull forward or back up onto the track off of the turntable. Same thing happens in polar coordinates. This is the direction that you point the train, this is the direction that you drive it. And by the way, this theta is in standard form from the positive x-axis. So 3 pi over 4, I start at 0, I go around to 3 pi over 4, and then I drive out 2 concentric circles. So 1, 2 puts me right there. That is the point 3 pi over 4. Okay, now there are coterminal points based on coterminal angles. I could also write 3 pi over 4 as 2 5 pi over 4. excuse me, to negative 5 pi over 4. So in this case, I start at 0, I go in the negative direction, 5 pi over 4, and then of course I drive out 2 concentric circles, which puts me in exactly the same spot. As you can imagine, there are an infinite number of ways to write 2, 3 pi over 4. You could also write it as negative 2, negative pi over 4. So I'm going to go negative pi over 4. I start here. I go negative pi over 4. I'm pointing in this direction, so I then back the truck up 2, which makes my r negative. All of those put you in exactly the same position in two-dimensional space. So now we're going to take points and we're going to convert them rather from polar to rectangular. And then we'll go back the other way. And again, all this is review. You can fast forward through this as much as you need to. You can rewatch, you can pause, whatever you need. All right, so if I was giving this test or this exam in class, I'd be giving you ordered pairs that are doable without a graphing calculator. I'd put that on the non-calculator portion. These are strange times indeed. So here's what we're going to do. We're going to work through it as if we have everything at our disposal. So the point, negative 3 root 3 is in fact rectangular. So I got this backwards. So now I'm going to go from rectangular to polar. We'll go back the other way in just a second. So rectangular to polar, this is rectangular form. Two things I need. I need r and I need theta. So I'm at negative 3 root 3, 3, which puts me here-ish in Q2. And a couple of things I want to think about. One is I want to imagine that I've got a right triangle here. And that my ordered pair are actually 2 of the dimensions of this triangle. So I've got negative 3 root 3 here. I've got positive 3 there. And then in order to get r, all you're looking for is the hypotenuse. So r is really c for the Pythagorean theorem. R is equal to the square root of x squared plus y squared. So I take r here, I've got the square root of negative 3 root 3, the quantity squared, plus 3, the quantity squared. So my r then is equal to the square root of, this is 9 times 3, that's 27, plus another 9, that is 36. So my r is 6. Now I just need to get theta, and I'm choosing triangle sides, which will give you a convenient trig ratio. Obviously, if this is my theta prime, if you remember back in the day, that's actually my reference angle based on this theta right here. Actually doesn't matter in this case. I have the opposite and the adjacent. So I have the tangent of my theta prime then is going to be equal to 3 over 3 root 3. You could put a negative on there if you like. These cancel. That is 1 over square root of 3. That means my theta prime is going to be pi over 6. But it needs to be in standard form. Obviously, it's in Q2, so that means my theta is going to be equal to 5 pi over 6, which now means the ordered pair of negative 3 root 3 in polar form is going to be equal to 6 5 pi over 6. Hope you can read that. Kind of looks like a 4. Let's redo this. 6, comma 5 pi over 6, and that's it in polar form. All right, going back the other way. All right, now let's convert from 5 pi over 6 into rectangular. Now, if I take a look at this drawing that I have here with this right triangle in Q1, just a generic triangle relating x to y to r with your theta there. If you take a look at the x, and this also relates to the unit circle where r is equal to 1. If I take the adjacent over the hypotenuse, that is the cosine of theta is equal to x over r. And if I take the sine of theta, I get the opposite over hypotenuse, which is y over r. So then it makes sense that x would be equal to r cosine theta, and my y is equal to r sine theta, which is why the quadrant angles, the ratios rather, of the quadrant angles are given by the cosine and the sine for x and y respectively. It's just that your r is equal to 1, but this is handy when I'm converting rather from polar to rectangular. And that's really all you need to do, except just calculate it, right? So going to rectangular, my x is going to be equal to 3 times the cosine of 5 pi over 6, and my y will be 3 times the sine of 5 pi over 6. The cosine of 5 pi over 6 is square root of 3 over 2, so this is 3 root 3 over 2. It's also negative since I'm in Q2. And then the sine of 5 pi over 6 is positive 1/2, so this is going to be 3/2. By the way, 3 5 pi over 6, point in the direction of 5 pi over 6, I go out 3 concentric circles, which roughly checks with where I'm at in rectangular form. It actually checks exactly, but at least you can check for reasonableness, looking to see that your rectangular coordinate is in Q2. All right. All right, the next section we're going to convert equations now, and we're going to start by going from rectangular to polar. We'll start off with just some easy ones here. Let's say I've got x is equal to 2, vertical line at x equals 2. When you're going from rectangular to polar, I'd like you to solve for r for every single one of these. I'll show you what I mean in just a second. So here's what I'm looking for. I'm looking to convert rectangular equations into a common or a polar form that you know. So x and 2, I can take my x out. I can just replace x with what it is. And in the previous page here, we had r cosine theta being my x, and that's equal to 2. And again, I want you to solve for r. So r is equal to 2 over the cosine of theta, also known as 2 times the secant of theta. And that would be your polar form. R is equal to 2 secant theta. All right, how about a conic section? This would be a circle. It could also be an ellipse, right? When the major and minor axis would be the same. So we're going to go through the same process as the previous example. I start off by taking out the x and putting in r cosine theta. There's 3 squared. Take my y out, that's r sine theta. Quantity squared is equal to 9. Foil out this first term here. This gives me r squared cosine squared theta minus 6 r cosine theta plus 9 plus r squared sine squared theta is equal to 9. Let's see here. These 9s cancel. I think what I'll do is I'll move this to the other side, and I will factor out an r squared. So I hope you guys are with me. If I factor out an r squared out of this term, then and this term, I get r squared times cosine squared theta plus the sine squared theta. That's equal to this term to the other side. That is 6r cosine of theta. We're close there. If you think about the Pythagorean identity, this goes to 1, which leaves me r squared is equal to 6r cosine theta. This is the only time you're going to want to do this. Generally, you never divide by a variable. I'm going to divide both sides by r, and I get r is equal to 6 cosine theta, which is going to be the polar form of this rectangular form of a circle. All right, now let's go the other way. Let's go to polar to rectangular. And if I'm going to polar, I want to solve for r. If I'm going to rectangular, I want standard form. Hope you can read that. So if it's a hyperbola, I want you to put it in standard hyperbola form. Straight line, solve for y, etc. Start off with an easy one here. Let's say I've got r is equal to -2. Remember that r, using the Pythagorean identity, is nothing more than the square root of x squared plus y squared is equal to 2, which is close to standard form. I'm going to square both sides. I've got x squared plus y squared is equal to 4. It is a circle. If you think about it, that makes sense. Here I've got a radius of -2 regardless of the theta. So it's 2 units out, which creates my radius, which is √4 as well. So this would be my answer in rectangular form. All right, here's an example that we looked at earlier. I've got r is equal to 3 secant theta. I'd like to use sines and cosines, so let's do that. Let's move that secant to the bottom. That's r is equal to 3 over cosine theta. I'm then going to move this over to the other side. That's r cosine theta is equal to 3. R cosine theta, if you recall from a few screens ago, was equal to x, and that's x is equal to 3. Vertical line at x equals 3. You are done. Done. All right, let's take a look at this one. These two are super close. They need r's, and it wouldn't hurt to have another r over there. I'm going to multiply everything then by r. That gives me r squared is equal to -3 r cos theta minus 2r sine theta. And then I can start replacing r's and thetas with x's and y's. R squared is x squared plus y squared. -3r cosine theta is -3x, and that is minus 2y. And then I want to put this in standard form. I'm going to take these two things, move them to the other side. That's x squared plus 3x plus y squared plus 2y is equal to 0. And now I want to complete the square for both of these. Take 3, cut it in half and square it. That's plus 9/4. 2, cut it in half and square it. That is plus 1. I have to do the same to the other side. That is 9/4 plus 4/4. That's going to be plus 13/4. And then I factor. So this will be x plus 3/2 the quantity squared plus y plus 1 the quantity squared is equal to 13/4. And of course I'm going to divide through by 13/4. That gives me 4 times x plus 3/2 the quantity squared over 13 plus 4y plus 1 squared over 13 is equal to 1. And that's your ellipse form in rectangular. There's your answer. All right, one last thing that's a little confusing. Theta is equal to pi over 6. Without actually importing a picture of a polar graph, I've got pi over 6, regardless of r, looks something like that. That's for positive r's. I could also have negative r's, so it also goes that way as well. That is a straight line. The y-intercept of 0 as I work toward rectangular. So a little trick here, what I'm going to do is I'm going to tangent both sides. I get the tangent of theta is equal to the tangent of pi over 6. And why will I use the tangent? Because tangent is sine over cosine, and I'm moving closer to what I need in rectangular form. That's going to be 1 over the square root of 3. Now, the left-hand side is close. I just need r's, so I'm going to multiply it by r over r, which is okay. It's just multiplying by 1. This gives me then y over x is equal to 1 over the square root of 3. I cross-multiply because I want it in standard form. That is y times the square root of 3 is equal to x. That means y is equal to 1 over the square root of 3x. That's it. That's a rise of 1, a run of √3. All right, guys, that'll get you through at least the first half of the homework. I'm going to cut this right now, and I'm going to create another one on graphing polar graphs with tons of shortcuts. You might want to check that out. By the way, you're going to be taking this test, as you know, open book, open note. You can always make an r theta table, so if you don't think you need it, don't watch. Have a great day. Hope to see you soon.